The topic of today's webinar is the LiveFront project, which is a project co-funded by the EU LIFE program. It's a project to remove the barriers for hydrocarbons, especially in standards. In today's webinar, which is the first in the series of the LiveFront webinars, we will tell you a little bit about the project objectives, the progress so far, and also how the interested parties can join and contribute to the outcomes of the project. So as you can see today, we have a lineup of 4 speakers. Dario, who's sitting right next to me, will tell you a little bit about the objectives of the project. I will give you a brief outline of the progress we've done with the literature review and the ongoing market survey. Then we will hear from Joachim from AIT Deutschland about the views from a heat pump manufacturer. And Daniel Colbourne will tell us about the new approaches for determination of maximum hydrocarbon charge size limits. So without further ado, this is just to add to my introduction. As I said, I'm the manager for market development at Checo. I've been with Checo since 2011. And today I'm leading the company's market development team, which focuses on market research, policy analysis, and funding projects for natural refrigerants. Next to me is our speaker, first in line, Dario, who manages the EU-funded projects LIFE and Horizon 2020. He's a graduate in development economics and European integration. He worked in Italy and Portugal, and before joining Checo, he was also working for the Executive Agency for SMEs of the European Commission. So Dario, the floor is yours.
Thank you, Clara, for your introduction, and good afternoon to the participants of our first webinar about the LiveFront project. Indeed, I am working on LiveFront as project officer with Checo, and my presentation will provide you with a general overview of the project activities. To start with, FRONT stands for Flammable Refrigerants Options for Natural Technologies. And as my colleague Clara was just saying, this is a project that is co-funded under LIFE, which is the European Union funding scheme for the climate and environmental action. More in particular, it refers to the climate change mitigation framework. The project itself is structured into 7 actions that internally we call work packages that are complementary to each other. It means that they are running parallel, and the data and the information that are collected progressively are shared among all project partners at all time. I invite you to have a look, also the project website at livefront.eu for further insights and further information. The project was started last summer in June 2017 and will last for 3 years, for 36 months. That is the longest execution time for a project under the LIFE framework. And so it will last until the summer of 2020. There are 6 project partners involved: Checo from Belgium, that is the project leader, ECOS from Belgium as well, 2 project partners based in Germany, AIT Deutschland and HIT, that are here represented by the other 2 speakers, Joachim Moll and Daniel Colbourne. A partner comes from Austria, AHT, and one from Sweden, NIBE. The main objective of the project is to remove barriers posed by standards for flammable refrigerants in the heating and cooling industry, with a particular focus on the European market. More in detail, we aim at supporting the standardization process for flammable refrigerants and hydrocarbons, both at the European and international level. We aim at increasing the safety of applications like heat pumps and other devices in air conditioning and refrigeration that are using flammable refrigerants. We want to increase the availability of alternatives to replace HFCs, also because in light of the F-gas regulation of 2014, HFCs will have to be drastically reduced in Europe by 2030. So more in general, we are supporting the European Union's 2030 climate agenda that is envisaging a a drastic reduction in greenhouse gases emissions, an increase in the use of renewable energy sources in Europe, and an improvement in the energy efficiency in the entire European Union. How to reach these objectives? We have basically different project outputs that because we are working on many fronts at the same time. For example, we are indeed working on public reports and public databases, collecting data for drafting requirements for standards and flammable refrigerants. We are and we will participate in standardization meetings with key stakeholders, both from the European institutions and the industry. We are conducting experiments and lab tests on leakage size and leakage rate. And in light of all these tests, we will be able to provide our industry partners that are participating in the project, that is AHT, AAT Deutschland, and NIBE, with key insight on how basically produce safer and more efficient devices using flammable refrigerants. Moreover, we aim at reaching a wide number of stakeholders that are working with hydrocarbons and flammable refrigerants. The target will be 20,000. And some of these, the more interested of these, are also invited, strongly invited, to join the Standard Action Group front. More in detail, the Standard Action Group front is a group composed of around 50 people that are interested on a voluntary basis and for free to collaborate and contribute to the deliverables of the project. In particular, their expertise in the heating and cooling industry and in the use of flammable refrigerants will be an important input for the development of the project in different stages. We invite, as I was saying before, invited stakeholders, interested stakeholders to participate in this group. They can come from different sectors, from academia, from trade unions, from manufacturers. So in case any of the participants of our webinar were interested in joining the group, I would recommend to visit our website, livefront.eu. In the section Get Involved, you have the link in the last row of the slide. And basically, clicking on that, you will be reaching this page in which, clicking the button Join the Standard Action Group, you will be redirected to a page containing a very short questions about your motivation and interest to join the project activities. By doing that, you will receive afterwards a password and a user ID in which you will be able to, with which you will be able to access a private section of our website and to share your ideas, advices, and suggestions with us and with all the project partners. So I think this will be a great experience also for you to get more, to increase your knowledge about the use of hydrocarbons and flammable refrigerants in the European market, and also to learn from project partners and to exchange key ideas. Your contribution by joining this group will affect all the project actions that will be the next topic of my presentation. Indeed, as my colleague Clara will explain you in a little bit, we already completed a literature review to understand the current state of play of the use of flammable refrigerants and their standards in the European market, while a market study is currently ongoing, also through an online survey that we invite you to fill in. And with this market study, we aim at understanding in a better way how the manufacturers and other interested stakeholders are using hydrocarbon refrigerants at the moment, what are their expectations for the future, especially in the European market, and how they foresee the evolution of the standards within the European Union. Another very important project action is the one conducted by HEAT primarily, that includes lab tests and experiments on the leakage size and the leakage rate. And in particular, data here are collected in order to create also public databases that will be accessible. This data and the databases and information will be important, as I was mentioning before, to contribute to create safer and more energy efficient products, and also to minimize the risk in case of an increased charge size, which is one of the most important topics when talking about applications using flammable refrigerants. The last project action is the one regarding the standardization process and the capacity building. So as you may imagine, and as you may have already understood from this short introduction, in this case, we are targeting the drafting of requirements for flammable refrigerant standards, and a key role in this will be played by ECOS, that is a project partner primarily involved in this part of the project activities, and by the Standards Action Group front, and therefore your contribution will be important also to understand your expectations and your understanding of the market and of the standard situation in order to foresee the possible evolution in the future. So I hope you enjoyed this short but I think exhaustive presentation about the project from a general point of view, and now I will give the word back to my colleague Clara to talk more in detail about the literature review and the market study. Thank you.
Thank you very much, Dario, for this quick introduction. Indeed, this project is quite complex, but the objectives, I think, are very clear, and that's removing barriers for hydrocarbons in standards. So all these activities should be contributing to the ongoing revisions of the standards at the European and international level. So as Dario said, joining the forces also with the interested stakeholders outside of the project consortia is very important, and we encourage your participation. So moving on to the next part, I would like to tell you very shortly about some parts of the projects that we have already completed or are in the process of working on. So one of the first things that we've looked at within this project was the review of the current standards to see what is the status when it comes to flammable refrigerants for different product groups. And what we've identified was that the primary barriers related to flammable refrigerants in safety standards are mainly linked to refrigerant size limits. And these limitations can take shape as the charge size limits for human comfort, restrictions for systems below ground. There is also the 150 limit for systems that are installed without any restrictions on room size, and also charge size limitations for large systems. The current standards, however, do not take account of different mitigation measures for flammable refrigerants, and these mitigation measures could increase the allowed refrigerant charge size while maintaining the same level of safety. So the different risk mitigation measures that were identified include the following that you see, such as improved system tightness, systems with integral airflow, charge leak test methods, housing design, sources of ignition test method. And I'm sure that Daniel will tell you a little bit more about these during his presentation. There are revisions of some standards currently ongoing in relation to hydrocarbons, and these have potential to open up opportunities for these refrigerants globally. Namely, the international standard for commercial refrigeration is currently being revised, and there is a proposal to raise the maximum charge size limits for flammable refrigerants. What that would mean, for example, for propane is that the current charge size limit of 150 grams in a single refrigeration circuit could be increased to 500 grams. The final amended standard is expected to be published at the beginning of 2019 if there are no difficulties in the revision of this standard. So that is the most optimistic scenario. Another standard that is currently being revised for air conditioning and heat pumps, there is a proposal to increase the allowable charge size for flammable refrigerants by implementing different mitigation measures, but keeping the maximum charge size. For the revision of this international standard, the timeframe is not as clear, and the experts that are involved in the process of the revision of this standard are basically saying that the amended standard is expected in the timeframe of 2019 to 2022. So it's really difficult to say from today's perspective when we can see a revised standard. Now moving on to the market survey. So because we want to see what is the current uptake of hydrocarbon-based products and what could be the potential impact of standards on the uptake of hydrocarbons in the future, we are conducting a market research as part of this project, and we have launched a survey on the 12th of March, which is running until the end of April, that looks at the availability of hydrocarbon-based products and also the potential impact of revision of standards. The results of the survey will be available with the release of the market research study in early September. We invite all interested participants, such as systems and component manufacturers, end users, research community, and others, to join and contribute with your views. Just to highlight, the results of the survey will be anonymous, and we will only publish the aggregated data to keep the confidential information away. You can join the survey by clicking on this link, and this presentation will be available afterwards, so you can look at it after. I would also like to share with you some preliminary results of the market survey. As I said, it's still ongoing, but we can already identify some trends from the survey that we've been running since mid-March, because we've received 165 complete and 237 partial responses so far. When it comes to location of organizations, it really varies a lot. I would say mostly they're coming from Europe, but we see also a lot of companies and individuals responding from other countries like Australia, USA, or China. We also see that it's mostly large and small companies. From the respondents, 50% of those that responded to the survey already work with hydrocarbons. But we also asked those that do not yet work with hydrocarbons about their plans, and 50% of those said that they start to work with hydrocarbons in the future. Then we were also interested to see what is the time frame for their plans, and most of them answered that they're planning to start working with hydrocarbons before 2020. So it is expected that in 2019-2020 period, we will see a major shift to hydrocarbons. We were also asking about the use of multiple refrigeration circuits in systems that companies are selling or that end users are using. Because of course, this is an area that is highly affected by standards. And if higher refrigerant charges are possible according to industry standards, then you would not have to use multiple circuits. So what is the situation today? 50% of those that work with hydrocarbons today indicated that they manufacture or they have acquired systems with multiple refrigeration circuits. As you can see, most of them are using 2 refrigeration circuits, but it's no exception also to use more than 2. We were interested to see what would be the impact of revised standards that would allow higher hydrocarbon charges. So we asked what is the share of hydrocarbon-based products in companies' portfolios today. And as you can see from the graph on the left side, majority, which is about 30%, said that the share of hydrocarbon-based products is about 1 to 5% in their overall portfolio. Now, when we asked what could be the developments within 2-3 years from now, by 2020, if standards allow higher hydrocarbon charges, the situation will shift quite rapidly, because close to 31% of respondents indicated that the share of hydrocarbons will be 76 to 100%. So the situation from today will change quite a lot. Now, if the standards are not updated by 2020, then 60% of the respondents said that the share of hydrocarbon-based products will be below 25%, but 21% still expect to have 76 to 100% share of hydrocarbon-based products. Overall, we can see that the revision of standards will have a major impact on the introduction of hydrocarbon-based products. We also asked the respondents whether they would be willing to work with higher hydrocarbon charges. And the answer was quite reassuring, because 2/3 of the respondents said that they would be willing to work with any charge as long as safety measures are taken care of. So this will be the role of the people participating in the standardization processes to ensure also that the revision of standards is taking place as expected, because companies are indeed already preparing for this change. Now, this concludes my part of the presentation, and now I would like to give the floor to Joachim Mau. So Joachim studied mechanical engineering and specialized in fluid and thermodynamics. He started working with refrigerant circuits in 2000 when he joined Rittal, and there he developed cabinet air conditioners with CO2 as a refrigerant. Since 2010, he's been working at Alpha Innotec, which is today AIT Deutschland. And he is also a member of several associations and different working groups, especially focusing on heat pumps. So I will give the floor to you, Joachim.
Thank you, Clara. Hope you can hear me good.
Yes.
So, oops. Hello, everybody. Again, also from my side. Yes, it's a pleasure to talk to you a little bit about our motivation to join the project, and I will just show you in 2 slides what's the reason behind it. But before, just allow me to give me a short introduction who we are, AIT Germany or AIT Deutschland. For those who do not know us, with a R&D in production in Germany, but we are part of Europe's largest heat pump manufacturer, the Swedish group NIBE, and we are selling heat pumps in mostly in Europe, but chillers also worldwide, and with a staff only for AIT of 500. But let's come to our motivation. First of all, I have done a similar presentation a few weeks ago in Brussels together with Clara. The F-gas regulation, I would say that's one of the reasons why we are speaking here. We absolutely support this, but we have to consider a few things. Yes, we are producing already heat pumps with natural refrigerant R290. And I wrote here in my presentation, wherever it is possible. Because in a lot of applications, we heard about it just a few minutes ago, regarding to standards, we are not allowed to use them at the moment. We have experience, 7 years with heat pumps with hydrocarbons, and a lot of units are sold in different markets and already used with, I would say, working well with a good success. But of course, if you're looking to heat pumps, there are a few boundary conditions we have to consider, and in quite a lot of countries, noise emissions become more and more important, and that's a reason why we have to go with some of the heat pumps inside of the building. And then comes the stop, because as we heard before, the refrigerant amount which is allowed inside of a building, it's very low, 150. If we are lucky, 500 grams in the future. Just to give you imagination where we are today. In the heat pump you see here on this picture, we have roughly 1 kilogram of hydrocarbons, R290 within the heat pump. So, as already mentioned, the existing standards do not allow or make it very difficult for us to use A3 refrigerants where R290 belong to at the moment. If you take a look on the different standards, I would say at the moment it's very, very difficult, or to say it's not allowed to use these refrigerants inside of buildings. Of course, the chemical industry offers new refrigerants. We have a lot of them now. They are listed A2L, but our issue is the existing standards do not reflect sufficient enough the new refrigerants. And we should never forget, I wrote here, they have a medium GWP. I think all of you know that, for example, A2L or the normal refrigerants, slightly flammable, are in the range of 600 to 800. There are only very few which are below. So it's a question of time until, we have to go to another one. And that's the main advantage, I would say, for example, for R290, which has a very low GWP, somewhere in the area of 3. So this is a future-orientated refrigerant, environment friendly. And that's also the reason why we said we support this project, we're joining this project, because we have to do something. We cannot always complain about what we do not have. We have to work on it. And from our point of view, standards, they should support natural refrigerants, even if they are A3, in a normal and good way. I think in one of the slides before it was written until safety measures are okay. That's definitely what we want to have in the future. But I would say we have to go on a safe way to higher filling or charges of refrigerant inside of these units. And that's one of the motivations we have, or the main motivation why we are joining this project. And I would say Daniel will tell you a little bit more about the results, what we have found out afterwards. So I would say that's a good way. And that's the reason why we are participating in this project. And let me finish my short presentation with a sentence: let us work on supporting natural refrigerants, because we believe that this is the future and we have to find a way to bring them good in the market, good and safe. Thank you.
Thank you very much, Joachim. So you can stop sharing your screen.
Yes, I will do. Oops.
Okay. Thank you very much, Joachim, again. I think your perspective as a heat pump manufacturer is very interesting, because indeed you are working with the technology on a day-to-day basis, and AIT Deutschland is actually one of the leaders when it comes to hydrocarbon-based heat pumps. Next one, we have Daniel Colbourne, who specializes in environmental performance and safety aspects of alternative refrigerants and systems. He works on behalf of different organizations, including GIZ Proclima, HEAT, UN agencies, and manufacturers and end users. He's a member to different organizations, UNEP Refrigeration Technical Options Committee, and also different standardization committees and bodies. So Daniel will tell us a little bit more about the alternatives way for setting the maximum hydrocarbon charge limits. So Daniel, the floor is yours.
Okay, good afternoon, and thank you indeed for the opportunity to make this presentation. Unfortunately, I was put on last, which means that the half hour I would like to spend going through this presentation isn't available to me. But nevertheless, I will try to go through it at a slightly faster rate. As was mentioned by the previous speakers, a large element of this project is to try to investigate and understand and develop better methods for establishing larger charge size limits for R290 and other hydrocarbons indeed. So what I want to do in this presentation is just dip your toes into some of the considerations and concepts that we're looking at, and that hopefully in the future we'll be able to elaborate on. So Joachim provided some clarification on this problem, and I have a graph here just to help elucidate it a little bit more. On the left axis, we have the R290 charge size, and on the x-axis, the cooling capacity of the equipment. And the data points show various air conditioning equipment were it to be charged with R290. And the orange lines show the upper bounds for how much refrigerant is permitted according to the current safety standards in air conditioning equipment. And what you can see is that for almost all products, especially the higher efficiency ones, it's way beyond what would be permitted today. So the idea is for air conditioners and also to the commercial refrigeration to try to bring the limits up above what is currently permitted today, so that a wider range of equipment and higher efficiency of equipment is permitted. I just want to illustrate in this slide, and you can look at the other points later, but this sort of main center image clarifies one of the inconsistencies and daft outcomes of what we see in the current safety standards and the way that the charge limits are calculated. So, for example, on the left-hand side, you have let's say a floor standing air conditioning unit that may be classed as for comfort purposes. And here you're only allowed about 200 grams of R290. Whereas if you have almost exactly the same type of equipment used for other purposes, for example, data center cooling, you'd be allowed up to 1,100, 1,200 grams. Everything's exactly the same, except the requirements. So this just sort of identifies some of the nonsense that we currently experience. The reasons for these are myriad, but just to give you a little taster, there's a number of assumptions that are embedded within the current charge size limits and other requirements that are based on rather tenuous assumptions. So, for example, it assumes that the entire, or under some requirements, it assumes that the entire charge or that the entire charge leaks out, which of course it doesn't. It assumes a constant refrigerant leak rate, which of course doesn't happen. It assumes extremely improbable leak hole sizes or leak rates, let's say. Also that rooms are completely gas tight, which of course they aren't. In some cases that leaks produce a homogeneous mixture throughout the room, which of course they don't. And also in some elements, there's an assumption that the refrigerant that comes out of the equipment is pure refrigerant, whereas in fact, we find that it's already pre-mixed significantly. So there's a number of these assumptions that have probably led to these various dubious charge size limits. So what we decided to do was sort of go back to the beginning and try to think about this whole issue on a fundamental basis. So the main issue is the risk of ignition. And then we say, well, what are the elements that contribute to that risk of ignition of flammable refrigerants or A2 or A3 refrigerants? So there's the likelihood of the leak, which is affected by system tightness and the location of the parts. The occurrence of ignition sources, which need to be addressed inside the equipment, or, okay, we assume some nominal values outside. But then most significantly, the size of the flammable volume. And that's affected by the airflow, either forced or natural, the housing geometry, the height and location of the system parts, assumed leak rates, the size of the room or the environment, and of course the mass released. So as part of this work, we're going through all of these different individual elements and trying to understand the implications and how those can be addressed or integrated into charge size requirements. So the concept that we're looking towards is follows this sort of logical progression. So first of all, system characteristics, obviously including mitigation features, external conditions, subsequent leak hole size, and the frequency of given sizes. This then leads to a certain released mass and mass flow rate, then into the equipment housing or enclosures, and this causes mixing and then flows out of the enclosure. And then ultimately it leads to a certain concentration on the floor or within the room, which can be then used to determine the either the allowable refrigerant charge to avoid the LFL or what the room size conditions should be. So we're sort of taking these various steps and examining each of these steps to try to understand the processes better and try to develop new requirements arising from those. So taking leak hole size, for example, on the top right graph, you can see just a plot of what the assumed leak rates are amongst the various safety standards. And ultimately, it's the same equipment or the same system, pretty much the same design, but there's a massive variation in different assumed leak rates. And you know, this just doesn't really make sense. So what we're looking at is a sort of more probabilistic approach, where, for example, if you have longer leaks, you might, longer piping, you might assume across that entire length of piping for a given frequency, a greater hole size. And then there's other parameters such as pipe diameter, pipe thickness, the number of components, the types of components, particular manufacturing quality methods, external conditions, impact, and so forth. So in the end, we're developing a correlation to determine the hole size as a function of some nominal leak frequency, and then all of these other parameters that will contribute to a particular hole size. And I think Dario and Clara mentioned before that we were developing a database of leak hole sizes. And that database will fill into this correlation and providing a high level of confidence in the determination of hole sizes for different leak frequencies. And for this reason, we again invite, or strongly invite, encourage members of this action group to contribute to it. Moving on from that, once you have your given hole size, you then need to determine the leak rate from that. And we've done a large number of experiments to analyze this. And in summary, what we find is that for almost all leaks, the majority of the refrigerant that comes out is released under choked conditions, sonic flow. And this graph on the top right sort of indicates that. So it's reasonable to assume, or to use sort of this classical choke flow formula to determine the mass flux or the mass flow of a leak. But importantly, under whichever conditions that part of the system is subjected to. So for example, if all of your high pressure parts are outside, then you don't need to consider a sort of saturated vapor pressure of, let's say, 45 degrees C or 55 or whatever, occurring from leaks within the occupied space. And similarly, if systems operate in reversible cycles, then you may want to consider that. So this enables, so this approach is a sort of basic common thermodynamic approach that we use on a day-to-day basis, but helps us provide more confidence in terms of determining charge limits. And in this slide here, I'll just provide a few examples from the initial work. I won't go through that, but you can sort of peruse that at your pleasure later on. The next step, which is largely neglected from current safety standards, is the effects of the unit housing. If you look across almost all refrigeration air conditioning equipment, it all has different housings that contains the refrigerant containing parts. And this housing has a massive impact on what the concentration that comes out of the housing has, and thus what happens or what develops on the room floor. So we've carried out a number of works to examine these processes. So first of all, to characterize the mixing within enclosures. So I have some examples here looking at leaks from the top, the middle and the bottom of enclosures and how the internal concentration is distributed. The next stage, we then look at what the exiting concentration is from these various housings. So on the left here, we sort of take the case of an indoor air conditioning unit, and the bottom left graph shows the local concentration exiting the unit laterally across the opening. And what you can see is that there's a massive variation, and that variation also differs according to leak mass flow rate. The critical point here is that all concentrations that we ever measure are a fraction of what pure refrigerant is, in the order of about 10 or more. So that gives a strong indication of the influence of the equipment housing. On the right-hand side, this looks at the vertical distribution of the exiting concentration from a sort of mock display cabinet. And again, this provides useful characterization to help apply to some generic methodologies. And then this next slide, I won't go through it obviously, but it just sort of gives you a snapshot of the variation in floor concentrations arising from different enclosure or housing architectures. And you can see that there's a really wide variation. On the bottom right, I have data for the case of a so-called diffuser release. And you can see that again, there's a huge difference between assuming a diffuser and the result of a release coming from within an enclosure. And taking a lot of this data and just plotting simple relationships between the mean floor concentration at the end of the leak and the exiting concentration from the equipment, you can see there's a fairly robust correlation. The data in these two graphs is the same, but just different colored data points to show the effect of two different parameters. So on the left, we can see where you have a fan on or a fan off within the equipment, and on the right, it shows the difference between various small openings and the effect of various big openings. And again, as I say, you can see quite a strong correlation between these two parameters, and that leads us to sort of understand what parameters we can include in the charge size limit. Again, I sort of plot some of that data here, and this basically shows the variation in extrapolated maximum charge limits based on the sort of trends of the floor concentrations. And what you can see is that under some conditions, the maximum charge in this particular case may only be, I don't know, 250 grams, but in other cases, up to 1.2 or more kilograms. And all of that effect is solely due to the architecture of the enclosure. And this is very useful to understand, because then it can help us design enclosures to minimize floor concentrations. Another effect is, okay, so based on all of this, we drew a conclusion that we can determine the maximum charge limit based on these basic parameters. So some representative height, the room area, the LFL, and some factor F. And both the height, or the representative height, and the factor F can be determined according to each set of test conditions and correlated to the construction or the architecture of the given housing. What I show here is the initial outcome of our findings, and so you can see here this factor F has a fairly strong correlation between these two, between this the floor concentration and the exiting concentration. And what we found is that depending on the actual construction of the housing, we tend to have two different curves, and we're investigating that in a bit more detail to try to better understand it. But at least it gives us a good direction to follow. So finally, I have the sort of basic steps for the interim mesh method here on the left-hand side, and on the right-hand side, just a few examples to sort of show the result, or the result of the new approach compared to the existing charge size methods within the current safety standards. And again, I won't go through this in detail, but you can have a look at your convenience. So 10 minutes after my allotted deadline, I'll just come to the interim conclusions. So, as has been reiterated on numerous occasions, the current charge size limits for hydrocarbons pose a major barrier for a wider adoption of these refrigerants in all refrigeration, air conditioning and heat pump equipment. The wide variation amongst the various equipment and the underlying basis for the requirements are, okay, in my view, highly questionable and let's say excessively pessimistic. So there's a definite need to start redeveloping using the basic principles and physical characteristics of the equipment. So the new approach that we've described follows some logical steps, accounting for various quantifiable parameters that affect end concentration that can be dictated in terms of the equipment design and construction. And adopting these various characteristics also empowers manufacturers to rely on techniques other than room size and unit height to build safer equipment and to allow a greater refrigerant charge of refrigerant. As I mentioned, the method is still under development, and of course it will be forever and ever. But the more data that we have, for example, based on leak hole sizes, will help find the correlations, and further investigation in terms of understanding the effect of housing characteristics on exit concentration and subsequent distribution in the room will provide a lot of significant contribution towards that. So thanks very much for your attention. I'm very sorry it was extremely rushed and it went over time, of course. but I hope it provided some interesting information for you. Thank you.
Thank you very much, Daniel, for your interesting presentation. It just shows how much of a challenge is ahead of us to really open up the opportunities for hydrocarbons in standards. One question that comes to mind, we were presenting at the beginning the issues that there are with the current standards, saying that the assumptions are highly unrealistic and pessimistic. Can you explain very briefly, how did we end up in this situation? Why do we have all these unrealistic assumptions in the current standards?
Okay, there's a diplomatic and a non-diplomatic answer to that question. So I'll do my best to give the diplomatic answer. I would say that initially there had been very little research done on this subject, and when there's very little research done, there's not much certainty in terms of what requirements you present. So in the absence of good, reliable data, you choose the most pessimistic or conservative assumptions that you can, because actually you're really not quite sure what the outcome would be. So, like I say, I think on one hand, people feel more comfortable with very restrictive assumptions because they just don't really understand the significance and the consequences. I'll bypass the less diplomatic answer, but I sort of expect or hope that most people can make their own assumptions there. But I think now, because there's been so much work done recently and more work is planned, whatever requirements are developed will come packaged up with a lot of confidence in terms of, okay, what the effects of these charge size limits are in different system designs, in different system arrangements, different room conditions, and so on and so forth. So, the more work we do, the deeper the investigations we cover, the more reliable the conclusions will be, and the more robust the subsequent proposed requirements will be.
Mm-hmm. Okay, I think what's also important to highlight is that the companies working with hydrocarbons should really be participating in the standardization process, because they are the ones that have the expertise. And from what we can hear from different experts in the field, the companies working with hydrocarbons or other natural refrigerants are not as well represented in the standardization bodies and standardization committees. So this is also to encourage people to participate in these processes, because obviously things that don't happen by itself, and the participation of those that have interest in this area is really necessary.
Sorry, Clara, if I can just sort of make a point to add on to that.
Mm-hmm.
This issue about leak hole sizes, in my view, and I think most other people's views, this is the most fundamental issue to all of these requirements for safety standards. And we have a situation where some people say, oh yeah, pipe breaks happen all the time. All the refrigerant comes out in a few seconds. This needs to be accounted for. But then you talk to manufacturers of a lot of equipment, and they say, no, leaks never happen. Leaks never happen. So this is the reason why we want to gather, or why we want to develop this leak hole database, to try to really get to the facts behind this. Because at the moment, the discussion is so polarized, or let's say the evidence or the arguments are so polarized, and everything is just based on supposition and assumption and oh yeah, I was talking to a bloke down the pub the other day, and he saw a pipe the size of a golf ball. This doesn't help to progress these requirements. So the more partners we have, and the more leak holes we can add into this database, the much more robust outcomes we have, and much more confidence we have in terms of how systems should be designed, and if they're designed in a particular way, what leak hole sizes we can assume for them. Okay.
Mm. Yeah, thank you very much for that input. Now let's have a look at the questions. I see that a number of people have put in their questions. So we can start with a question from Xudong Bang. He's asking about the standards action group. He says he's filled out the form but have not heard any feedback. Yes, we'll make sure to get back to you as soon as possible, and apologies for not responding. There might have been some technical issues. We'll look into it. Menno van der Hof is also asking about the standards action group, whether it involves traveling costs or any other costs. Basically, the idea is that it's not requiring any additional cost in terms of traveling, because the meetings that will be held as part of the standards action group will be online. So hope that answers your question. Then we have another one from Kate Leon, whether the revised standards for air conditioning and heat pumps wait until after LifeFront is concluded. Well, if I may just quickly answer to that, actually the idea is that the ongoing work carried out under the LifeFront project feeds into the ongoing processes of the standard revision. So this is an ongoing process, and we're basically not sitting and waiting for the project to be finished, but we are proactively participating in the standardization meetings. And also the idea for the members of the standards action group is to support these efforts as well. Next question by Richard Fennelly. One US-based HVAC&R expert stated about flammable refrigerant safety in refrigeration applications: you've got to keep the condensers and evaporators clean and the fans operating. So this is an extract from Accelerate America from February 2016. And he's asking if this might be the standard advice going forward. So maybe Daniel or Joachim can answer this question. So whether keeping the condensers and evaporators clean and the fans operating.
It's obviously it helps. It's difficult to standardize on a product to say you've got to keep the condensers and evaporators clean forever and ever, because the manufacturer can't ensure that. But yeah, I mean, there's possibilities for obviously putting design features in to try to minimize the amount of filth that accumulates on these heat exchangers. But yeah, if you have some useful suggestions for this, then you know, please send them to us in terms of the actual requirements, and we can try to integrate them.
Thank you for that. Yeah, go ahead.
Maybe just a comment from my side. In addition to that, what Daniel said, that's absolutely right. Finally, it's always a question in the design of a unit that you avoid any kind of flammable mixture in a near or close to an ignition source. That's the main purpose. And if the fan is operating, this would help, and all of the others are clean. Yes, why not? But first of all, you should avoid any flammable mixture close or near to an ignition source. That's the main purpose, and that's you have to check from design to design.
Yep, thank you, Joachim. We have a few more questions, but not much time, so I will just select a few, and then we can also answer the ones that we don't take live. We can answer them in writing, and we'll get back to you by email. I'm just looking at a question from Steen Portmans. Are you planning on setting up a cooperative data mining where you gather actual leak rates based on direct refrigerant weighting and indirect refrigerant content based on operating conditions? This way, I assume you have stronger in-field empirical data on which types of setups are less sensitive to leaking. I think maybe Daniel, you can answer this question, perhaps in regard to the databases that we're setting up.
Yeah, that's sort of broadly what we're trying to do. Rather than measuring leak rates as such, as and when a leak occurs, get to cut out, and then we determine the hole size from that. For example, through mass flow through the hole under fixed conditions. So pretty much the same, similar to what you've mentioned here. But then it's sort of real empirical data, and also when this happens, we log the location of the leak, the type of system, the age, the location of that part of the system, and so on, so on and so forth. So this then comes back to this correlation that we're working on to help identify the frequency of certain leak hole sizes according to the construction of the system, the location, the materials, and so forth. So yeah, that's pretty much what we're doing, and you know, it's a really, really big task, and it requires as much data as possible because, you know, as you can imagine, each data point is pretty, let's say, expensive or difficult to obtain. So the more input that we can have on this, the much better the outcome would be.
Mm. Did you want to add anything, Joachim, on this point? I see that you
no, not at the moment.
Okay. There was another question from Menno van der Hof. He says the presentation is mainly focused on hydrocarbons and in split or non-cellular applications, but he is interested in applications below ground level or outdoor. So he says also there the charge limit may be restrictive, and he's interested to know whether the standards action group would investigate more appropriate charge limits for these situations. I understand actually this is the sector where Joachim is also active. You have heat pumps with hydrocarbons, which are outdoor heat pumps. But maybe Daniel can answer this, whether these applications are covered.
Actually, the presentation covered sort of more or less any equipment. It's just that split happened to be a sort of used as an example. Actually, we've had a lot of discussions over this below ground issue within the working group for EN 378, and we've sort of gone round and round in circles a little bit, but we seem to be converging on some agreements to how to resolve this particular problem. Okay, when you think about it, there is no reason for this below ground. It's just that people tend to feel a bit nervous about it. So we put a bit of extra padding in there to try to address it. But it might be useful if we sort of had a discussion bilaterally, so I can sort of understand what your particular issues are and how this could be potentially addressed.
Okay, very good. I see that we're running already a little bit, but Joachim, please go ahead. You wanted to add something.
Maybe Clara, if you can just propose to make the contact to Menno for me, because of, yes, we have some knowledge about distances and things like that, so maybe I can discuss it with him afterwards.
Okay, yes, I will be happy to put you in contact.
Thanks.
Thank you. I see that the time has already run out, and we have not answered all the questions. It just shows that there's a lot of interest in this topic, and we'll be looking into these questions, and we will be getting back to you with some answers in writing. Apologies, we did not manage to answer all the questions, but if you have some additional questions or comments, please don't hesitate to contact us at info@livefront.eu. I would like to thank all the panelists today. Thank you very much for your presentations, and thank you all for listening in. I hope you found the webinar interesting, and I hope you will be joining us for the webinars that will be coming in the future. And also, hopefully some of you will be joining us for the Standards Action Group. Just to recap, the recording will be available to you in a few days, together with the presentations, and it will also be uploaded to the LiveFront website. So with this, I again thank you all for listening, and have a good afternoon.